Well, welcome everyone to the final event of the year, where we'll be going over what happened across this year. We'll then have the three winning teams give 15-minute presentations talking through their project and how the team was structured. And then we'll have a look at what we're planning to do for next year's competition. So a bit of an overview. So this is the artificial heart competition where we're aiming to address the major problem of heart failure and hopefully build the next generation of cardiovascular engineering. And um, several of the students and academic advisors have been able to give us some very nice testimonials about how this competition is helping build a community across numerous countries around the world and interacting among them, developing business, technical, and professional skills that um, either are not available in your traditional education or are a good culmination of the summer event, and all for making a difference in trying to solve this issue of heart failure with a total artificial heart. So we started way back in 2021 through Monash University or Monash Young MedTech Innovators with two sponsors. Um, we then officially launched it in 2022 with just one team. And then last year was our inaugural competition with 9 teams, 5 sponsors. Um, and already then we had made quite a big difference in terms of the ISMCS, the International Society of Mechanical Circulatory Support, contributing to 18% of their membership and 20% of their conference attendance, where pretty much all the undergraduate students attending the conference were due to this competition. And then this year, we've had about 270 active students. 21 abstracts were presented at the conference in Japan. And now membership is composed from the Heart Hackathon group, 33% from the society, and 23% of the attendance at the conference was from the Heart Hackathon. So we had 9 teams that are presented here. And you can view on the web page, 8 of the teams produced short videos kind of summarizing their progress and what they have done. And we highlighted some of the achievements already in the finals, but we've had various teams get TV interviews or press releases, have won both within university best honors projects or best project awards, and even teams winning or shortlisted for awards on in national competitions as well as getting acknowledged by various important figures at major events. Which we've recently updated the news page on the website to highlight some of these achievements. So through the year, we had the preliminary report and total artificial heart symposium, which were not assessed in terms of determining the final award, but were given feedback. And then we also asked many teams to submit videos, and then we had the assessed final report and grand final in Japan. We had a total of 8 webinars across this year's competition, uh, ranging from patient journey to actual workshops on the V-Patient software, regulatory, early fundraising, and poster design. And then this year, we also introduced advisor consultations. So we had these 8 advisors, and many of the teams utilized this quite well through the competition. And we're hoping to continue and expand upon that next year. I'll then pass it on to Madhu.
Ethan. So moving on with the highlights of the grand final, to mention the event was a grand success. And we had 9 teams in total who fly down from different countries, as Ethan mentioned before. And there was room full of people, I mean, students, mentors, researchers, and industry representatives, with around 100 people exchanging their work and learning from each other. So also to highlight, in the right, you can see Sean is having a book. So he has launched his new book, the second edition of Mechanical, Circulatory, and Respiratory Support during the event, and it's up online now. So I highly recommend anyone who's interested in this field of MCS to learn and want to learn almost everything in one place. It's a go-to one. And also to mention, the royalty of the book is donated equally to ISMCS and ECMONet to support young researchers. And we also had like few interactive sessions. So the bottom right corner is the feedback session that is happening, which helps us to improve each year. And we had a lot of feedbacks this year, and it's good too. So we are trying to implement it and become better. And so the big thanks to everyone who has contributed to that. It's the next slide, please. Oh, so this is the local stats event that I mean, not event that happened during the break, and we also had the mini interviews during that time. So, um, is the next slide, please? Next slide. Yeah. So this is the social dinner, and it also was good to see how students got together at the end of the day. It's always a good indication of a successful event, I think. And moving forward, in the next slide. We had the posters, like more than 15 plus posters were presented in the ISMCS event from our Heart Hack team, and more presentation from Egypt and Romania teams on their work. And there's a session called New Technology and Techniques. In the next slide, you can see uh, either wet lab happening at the event as well. The photo at the right, fourth photo from the in the first row. So that's the wet lab that's happening parallelly in the event. So where the industry partners from different industry were demonstrating their models, and the people, students from the Art Hack were get to work with them, like hands-on sessions were happening over there. It was quite interactive. And this is the gala during the ISMCS. And first photo is like Sean's presidency. He's a president of ISMCS at the moment, and he's so proud of it. And that's just a dream come true. So next is in this gala dinner, we also got like few pictures of Team Bath, the winner of Heart Hack, and following with that, the poster presentation award. So Team Bath and New Team Thai has awarded the poster awards, and congratulations to them. Next, moving forward, next slide. So these are the special awards. Marvel's team got the most advanced design, and Team Monash Heart Hack got the most developed business plan award. And congratulations to them. And next, moving forward, the overall winners. So first place was given to Team Bath, and second place was CBU, and third place was Mending Broken Hearts. So congratulations to all the team winners, and they are well deserving. Now moving forward, winning teams will be presenting their final pitch. And so the format is like 10 minutes final presentation, and 5 minutes will be the team structure and how to be successful as a team. And at the end of all the three presentations, we'll be having like 10 to 15 minutes time for us to ask questions to the team. So for now, we'll be starting with Team Bath. Am I right, Ethan?
Yes, yeah.
Right.
We'll be
Yeah,
starting with Team Bath.
Team Bath. Yeah. So Team Bath will be giving their presentation now.
Cool. Can everyone see the screen?
Yes.
Okay, so we'll get started. So this is the final presentation that we presented at the Heart Hackathon, and it's modified slightly, like Madhu said. So we took out the commercial section essentially and replaced that with a bit about the team structure and how the team was managed. So we are Team Bath Heart, and I'll be going over, and my team will be going over the development of a novel total artificial heart. Today we'll be covering a number of things, including, like I said, team instruction, team structure, background, future work, the TBH24 design itself. Those two should be swapped around, but anyways, and then a conclusion. So to get started, and during the Heart Hackathon, we mentioned about intellectual property. So as part of protecting our intellectual property, we haven't disclosed much about our internal mechanism, and that's because we're figuring out ways of patenting our design. And as part of that, we don't want to disclose too much about it. So that's just a notice. So for those of you who don't know who we are Team Bath Heart. We are based in the UK, and we are the University of Bath's only medical engineering competition team, and we're designing a novel total artificial heart. Next slide. So we take great pride in the diversity of our group. So we now have a 50-50 split between male and female team members, and we have more than 80 students ranging from mechanical, electrical, chemical engineering, natural sciences, and many more, who are all contributing to one mission. And it's very exciting for us. Next slide. So in Japan, we had a nice split between our technical and commercial team. So they could each provide sort of a unique perspective between of all the work that they've done. So a bit about how the team is structured and just sort of advice and project management and whatnot. I'll go over that now. So we have these roles that are assigned specifically. Our team is huge. Like I said, we have nearly 80 people now, but within that, we've got specific roles, and the core team actually is around only 20 people. So that's much easier to manage. And this is sort of the breakdown. We have team lead, which is me this year, and I've handed over to the next team lead for next year. But I look over the technical and commercial teams, and each of those teams has a technical and commercial lead. Within the technical team, we always have at least 2 mechanical leads, 2 electrical leads, and 2 biology leads. And now we're introducing a lab coordinator as well to take care of our lab and build room and so on. And on the commercial side, we have loads of more specific roles because I think it helps give everyone sort of a purpose and know what their job is. So we have a business team, marketing team, and quality and regulatory team. And within that, we have specific managers who are responsible for certain tasks. So finance and sponsorship manager. We have social media, who take care of all the social media, branding, events, website. And then within quality and regulatory, we have a Q&R manager, an IP manager, and now we're introducing a sustainability manager. And all of these sort of just fall under the commercial team. And yeah, I kind of just play a hand in each of those roles sometimes, or just communicating with the technical and commercial teams and making sure that everything's getting done, or if anything is not getting done, then I will do it or we'll pass it on to someone else. So that's just sort of how it works in terms of roles. And then next slide, within the roles, we have obviously communication is a big thing. So to do that, we obviously have to have a lot of meetings and sometimes too many meetings, but they have to be done. So we have weekly general team meetings, and these are run by the team lead. And this is so that everyone in the team can get together and can go over updates, general updates, technical updates if needed. So it's a nice sort of weekly moment for everyone to get together. We have weekly technical meetings, weekly commercial meetings, and then also sub-team meetings if needed. So that would be social media team meetings and whatnot if they feel that they need them. But yeah, and then on top of that, I also introduced a monthly newsletter, which was sort of an internal newsletter that was distributed within the team so that everyone, on top of the general team meetings, people could be in the loop. And now we're thinking of widening that to our department so that everyone who's sort of contributed to the team can get involved, and potentially sponsors as well, because it's quite a nice thing to read. We also had a shared calendar. We have a job board in which we split like jobs, and jobs get assigned and get completed and whatnot. And then we also have kept strong relationships with our universities and supervisors. And this obviously we know that we're very lucky to have because we have a lot of help from our supervisors. And yeah, and it's important to keep that relationship going and make sure that, because they're the ones who kind of know what to do and what not to do. And then something that I introduced when I became team lead was sort of a feedback system. And I'm hoping that this continues. And it's basically a feedback systems for me and the leads to sort of go over. So I will give them feedback and things that they're doing well, things that they're not doing well, and I expect the same back. And then I ask them to pass on that same information and do the same thing with their leads. So it's kind of a nice monthly, or not even monthly, but every so often, whenever it's needed, review kind of system, and it helps sort of smooth things along. So my advice as a project manager is say yes to everything. I think one thing that I found, or that we found as a team, was that saying yes to everything, especially in the early days, because we are a relatively new team and so are the other teams in their universities. I think saying yes to everything, such as sponsorship events or meetings with the university or university events or anything to do with press releases, like we just said yes, even though it was quite time consuming. I think it really helped push our name and push sort of the work we've done. And then the next thing would be focused on recruitment. So when I was speaking to people at the Heart Hackathon, a lot of people were saying that they have trouble with handovers and handing over the knowledge from previous years. And we go through the exact same thing every year because, for example, the 8 of us, well, 7 of us are graduating now. So there's going to be a big gap between the knowledge that we have and the new team will have. So focusing on recruitment, and making sure that the handovers are good as well is quite important. So that's my next point. But you will always also need a bigger team, even though it might be harder to manage, but you can always have people to rely on in the end. And then you can kind of figure out who you can rely on as well. So that's quite important. And I think those two may not seem like they're quite important at the start, but they do end up being important in the end. But yeah. And then having a robust filing system. I say that even though we can't find any files in our filing system, but we do have a pretty robust filing system, and we document everything. So once we find something, we know it's there and it's sort of all stored, and we follow ISO 13485 or whatever it is. And we make sure that everything's sort of put in there so that at least everything's documented, and that makes the handovers a lot easier as well when it comes to it. But besides that, we do recognize that we have a lot of university support. So in the past, how it worked for us was that our team, we have a bunch of competition teams in Bath, but our team specifically would approach the department independently with a proposed budget, and then we would ask them for money. But now that's changed completely, and it changed right before we went to Japan, so quite recently. And now it works by fairly splitting the department money between all the competition teams, and that includes money and space. And that's based on several criteria, such as the budget that they have, the commitment and our contribution to the university, the diversity that we have, LEAF assessments, and equality, diversity, and inclusion. So a bunch of criteria, and we have to fill out this form and basically sell ourselves to the university. And they tell us kind of how much we're worth as a competition team, essentially. But that does help push us to do better and do a lot more. And I think it's a nice way to kind of make it fair for all the competition teams to have a fair chance of getting the money that they deserve. So that's a pretty good system that they've put in place very recently, and we're kind of taking advantage of. But yeah, we do recognize that we have a lot of support from the university as well. So now I'll go back to our original presentation. So a bit about why we're doing what we're doing and like our cause as a team. Cardiovascular diseases are the leading cause of death worldwide for both men and women, and there's a clear patient gap between the number of adults waiting for a heart transplant and the number of transplants performed. And this can lead to really long wait times, which means that patients are at risk of dying before a heart becomes available or can become too sick to have a transplant. And on top of this, as you can see here, the criteria for receiving a heart transplant significantly reduces the number of people who can actually get one. So this unmet clinical need is what has led us to our mission statement, and our mission is to develop a novel total artificial heart that is both long-lasting and effective. It must improve survival rates for patients with end-stage heart failure by reducing post-surgery complications and providing a better quality of life. This is what drove us to create TBH23 for the 2023 Heart Hackathon, and we evaluated this design and developed it further to create TBH24. And I will now pass on to Molly, who is our mechanical lead, to go into the details of the TBH24 design.
Thank you, Mansi. So at the beginning of our design process, we outlined our key requirements and determined our target patient profile, which we chose to be a 49-year-old male of average height and weight. From our mission statement, we knew we wanted our device to be long-lasting, reduce the chance of infections by removing the need for percutaneous drivelines, and reduce blood trauma to avoid hemolysis. A full list of design requirements, a few key ones shown on the screen, was developed based on a comprehensive needs analysis of all stakeholders, relevant regulations, and biological research. We then began the ideation phase using the Crazy 8 method to generate as many unique ideas as possible. We then ranked these ideas with a Pew's matrix with the TBH23 as a datum. The TBH24 design is a new and novel development from the TBH23, carrying over the use of artificial ventricles but replacing the string mechanism with a more reliable plate compression system. This has allowed us to reduce the size of the device by over 50%, in turn also reducing the weight. The compression mechanism squeezes the artificial ventricles in a way that mimics the native heart. This ejects blood around the body while avoiding stagnation in the ventricles. During diastole, the ventricles will fill passively, resulting in higher end diastolic volumes at greater atrial pressures, emulating the Frank-Starling mechanism. This means that the device can vary its left and right cardiac output without active control, reducing the risk of volume overload. The device is encased in a titanium alpha-beta alloy shell, split into 3 parts for ease of assembly, which will be laser welded together. A 2-part structure was designed to secure the Foldax trileaflet valves and attach the device to the body. The valves are sealed against a flange on the artificial ventricles and clamped down by housing attachments screwed into the underside of the top plate. Clips are then used to secure the polyethylene terephthalate connecting tubes for sutured atrial and arterial connections. The positions of these connections were determined using Vitonomy's V-patient software. We took one of the sample patient's virtual anatomy, whose profile was closest to our target patient, and transferred the position of the connection points into our CAD software. Due to the flexibility of our chosen graphs, this should be adequate to fit our target patient range. Extensive simulation work was done to validate and improve our design. We assessed the longevity of our internal components using finite element analysis software. An area of particular interest was the artificial ventricles during compression cycles. The maximum stress was found to be within our specification, however, we aimed to do further physical testing to verify this due to the complexity of the loading. To help our valve selection, we calculated wall shear and hemolysis index using computational fluid dynamics. It was found that the polymer valves led to lower shear stress than the mechanical valves, so we chose the polymer ones to integrate into our design. Finally, we used ANSYS Fluent to create transient models using pressure inlets and outlets to model the artificial ventricles. The animation on the screen shows a small stagnation point at the bottom of the ventricle, so therefore further iterations are required to try and reduce this. To further validate our design, we aim to prototype as many components as possible. Gravity casting with a wax mandrel was used to manufacture the ventricles out of polyurethane, which was chosen due to its flexibility, high tensile strength, and biocompatibility. The internal surface finish was assessed using a digital microscope, and it was found that PU60 had a better finish than PU30, with an average defect size of only 80 micrometers. The PU60 also produced less air bubbles. Our sponsor Autodesk provided us with great support for prototyping our casing. They 3D printed a version out of a clear resin for visual representation, as well as machining the top plate out of stainless steel for proof of machinability. Here you can see a 5-axis CNC machine that was used to achieve the complicated shapes and surfaces. Our biology team investigated material-induced hemolysis using horse blood. Due to malfunction of our rheometer, we used an orbital shaker with different samples of polyurethane in contact with the horse blood to compare the damage on red blood cells. As shown from the graph, the data suggested that PU30 had slightly better hemocompatibility, but we intend to repeat these tests with more accurate equipment. We also manufactured the internal mechanism of our design and built a test rig to validate the pumping function. Here you can see a video of it pumping water. The team has also developed our own mock circulatory loop, encapsulating both pulmonary and systemic sides, replicating the circulatory system's physical and hemodynamic conditions. We attached our test rig to the MCL and we were able to obtain pressure waveforms and flow rate, but due to complications of testing, these were not representative of the device's performance. I'll now pass over to Ben, one of the electrical leads, to discuss the electrical part of our design.
Thank you, Molly. So our design features an active control system that functions in addition to replicating the passive Frank-Starling mechanism, based on adjusting the heart rate by varying the actuation speed. The control system complements the native venous return system to circulate the correct amount of blood around the body. It's a priority-based control system using left atrial pressure as its primary control. When left atrial pressure is within a safe range, then aortic blood oxygen is used to provide finer control. The input sensors have all been tested within their operating ranges, and a test bench has been built for the pulse oximeter to ensure that it will function correctly within the low light conditions of the cardiothoracic cavity. This video shows how the inputs are affected by, shows how the heart rate is affected by changing system inputs. To prevent the use of drivelines, we have chosen to develop transcutaneous power transfer and communication systems. For communications, we have used ANSYS HFSS to develop a human body phantom, a 3-layer model of skin, fat, and muscle to measure the effects of their differing dielectric properties on the antennas. Using this phantom, we have designed internal and external magnetic spiral antennas, the design of which was recently published by a team member. These are designed to minimize induced tissue heating while operating at a frequency of 2.45 gigahertz. These cores have been manufactured and are currently undergoing testing with a physical phantom that we have produced to see how they're impacted by the different tissue layers. For power transfer, we have been using inductive near-field wireless power transfer to power the heart. 2 flexible cores have been designed, again using ANSYS HFSS, and manufactured. Testing of the system has produced 22.9 watts of transfer across the phantom at efficiencies reaching 60%. Thermal testing is currently underway to measure the generated heat of the electronics and the absorbed energy by the body to ensure our system does not produce excess tissue heating. On to future work. This figure shows the outline of the electrical system so far. We're looking to implement a full power system, including an implanted rechargeable battery to ensure the heart is continuously powered. Additionally, an antenna holding system needs to be developed to prevent misalignment, and alongside this, more thermal testing is required to develop the wireless power transfer system to ensure that induced tissue heating remains low enough to prevent any tissue damage. Finally, we're also looking to develop a user interface to provide information like battery level to the patient and to store vital data about the heart functioning for use by clinicians and engineers to maintain the long-term health of the patient. On the mechanical side, our primary focus is size and weight reduction. As you can see from the V patient's image, our current design clashes significantly with the left lung and diaphragm. We intend to use Fusion's generative design features to reduce the weight and size of our internal components, and we're doing additional research into alternative materials for the casing, such as biocompatible polymers and composites. There are also intended design changes for the artificial ventricles to remove the previously mentioned stagnation point, and we also intend to do life cycle testing on the ventricles to test the durability of the polyurethane under continuous compression cycles. We will continue testing on our mock circulatory loop to test the functionality of our pumping mechanism, including its response to varying atrial pressures. With the reduction in size of the heart, high pressure fluctuations occur within the casing, and so we're looking to develop a compliance chamber to minimize these. I'll now pass back to Mansi, who will conclude.
Thank you, Ben. Also, I'm sorry if anyone can hear a dog barking in the background. There's very loud dogs barking. Anyways, so to conclude, the summary of our design. This shows our target specification against what we achieved with our final design. And we have successfully designed, tested, and prototyped an artificial heart. So we are now really close to achieving our mission statement. And aside from this, we also thought it'd be nice to do a bit of Heart Hackathon feedback, which is in the next slide. And this is just us nitpicking because honestly, everything was amazing. But yeah, a bit of feedback similar to last year's closing event. So one thing that we thought of was releasing the assessment criteria and like any changes to the assessment criteria a bit earlier because they were released quite late this year. But granted, there weren't that big changes, so it was all okay in the end. But just in case, you know, for if there are big changes. And then we also thought that it would be nice to have more feedback on the final presentation itself, and potentially a second marker for each section of the report. I think it's great that there's a different person for marking each section of the report now, because it provides a different perspective, of course, and makes it fair for all the teams. But a second marker might be good, or some sort of justification for some of the marks that we are getting, because we were a bit confused by some sections being maybe much different to other sections, in terms of the marks that they got, and didn't really understand why. Then the other point that we came up with was that it would be nice to have a communications channel set up, and advertised for all the teams, so that we sort of have a communication point, way before the Heart Hackathon, and have one like throughout the year in case we're having any difficulties or just things to talk about, and preparation for the Heart Hackathon. So that ties into more opportunities to network with the other teams prior to the grand final. And finally, more opportunity for public questions after the final presentation, because I think there was 5 minutes of presentation time, but it might be nice to increase that question time, so that we can ask more questions, because I think a lot of people had a lot of questions, and it's good to have that feedback directly after someone's presentation. So yeah, that's it. But again, we are nitpicking because it's all amazing. So yeah, we'd like to thank our sponsors, our supervisors, obviously, who've been a huge, huge help, and any experts that have helped us along the way. And then obviously the Heart Hackathon for providing us with this amazing platform to compete in this competition, and for all of us to meet and work really hard on this project. So thank you so much. And we hope you enjoyed our presentation. Yeah.
Thanks, Team Bhatt, and thanks, Nancy, for the feedback. So we did take few of your feedbacks, and we have provided the solution in the following presentation. And also we'll try to implement the other feedbacks as well. And yeah, it's a good presentation and well deserving for the first prize again.
Thank you.
Yeah, thanks again. So let's move forward with the following presentation. Let's go with Team CBU. And other questions will be asked at the end of all the presentations for you guys. Yeah. So is CBU ready to present? Yeah, over to you guys.
Hey everyone, my name's Josh. I'll give our presentation, and then, like Bath, we replaced our commercialization section with a bit of info about our leadership structure. So we are CBU Cardiac Engineering, a fully undergraduate team. Sorry, hold on. A fully undergraduate team of over 50 scientists and engineers from California Baptist University in Riverside, California. My name is Josh Lute. I'm the president. With me is Gianna Lawson and Jessica Gordon. They're also on the call and they'll be presenting. And then our advisor is Matthew Jared Card. So cardiovascular disease is the leading cause of death worldwide. And without a permanent solution, many are left without options. And it's true that by the end of this presentation, over 600 people will have died from cardiovascular disease. It's this statistic paired with over 3,000 patients in the US alone awaiting heart transplant that we aim to build the world's first permanent total artificial heart.
Within this year, we focused on 5 specific goals: how to optimize low power consumption, reduce blood damage, pump 5 liters a minute, create pulsatile motion with a stroke volume of 70 milliliters, and fit within the heart cavity.
Pulse by CBU Cardiac Engineering is a novel biventricular peristaltic pump. Pulse 1 was highly successful as it was able to output as high as 5.6 liters per minute and was awarded 3rd place at the Heart Hackathon last year. Through research and development, we've been able to make 4 new peristaltic pumps, which led to our new tubeless peristaltic pump, Pulse 3. Our Pulse 2.4 design is a highly effective pump with an accurate native pressure of 125/90 millimeters of mercury, and impressive flow rates as high as 9.8 liters per minute and power draws as low as 7.2 watts.
However, without power, flow rate means nothing. We optimized our pump to be extremely power efficient. While Syncardia is able to pump 9 liters per minute at 40 watts, Pulse 2 pumps 10 liters per minute at 21 watts, making Pulse 2 twice as power efficient as Syncardia. The graph on the left shows power versus flow rate, showing how we increase in flow rate with power. We are able to draw power as low as 7.2 watts at 7 liters per minute. This is loosely comparable to bivocor's power draw, ranging from 6 to 17 watts at 5 to 12 liters per minute. However, if you extrapolate the trend line to 5 liters per minute, you find that we have a theoretical power draw of 4 watts, which is lower than both.
This was all tested in our CBU Garner mock loop. The Garner MCL 1.1 included a compliance chamber, pressure, flow rate, and power measuring capabilities. MCL 2.1 is being designed as a biventricular MCL and will incorporate all components of the MCL 1.1.
The two requirements that we met with Pulse 2 is having low power consumption yet generating high flow rate. The three that remain have a common issue within our tubing element in Pulse. Looking into the tubing, we saw that there was many issues with our tubing, a couple being limited stroke volume and longevity issues. From this, we searched everywhere and we have not found tubing that met all of the needs of our pump. Therefore, we dove into custom tubing research. We created composite materials and tested them under a mechanical fatigue tester, and after degrading them, we saw that we needed a new solution for the tubing. So we dove into tubeless design exercise that took 3 months, where we created multiple tubeless pumps, outputting as high as 8 liters per minute. And from all of this research, we have been able to craft a tubeless peristaltic pump. We'd like to present to you Pulse 3.
Pulse 3 is a biventricular toroidal pump that uses a magnetically levitated shuttle to gently move blood with minimal resistance. The shuttle separates 2 chambers, enabling synchronized forward and back strokes for the systemic and pulmonary flows. Ductile valves control inflow and outflow, while neodymium magnets and a central rail guide shuttle movement, minimizing contact points and hemolysis risk. Finally, an internal PTFE coating reduces friction and thrombosis potential. Then, made out of a certified biocompatible material, Pulse 3 takes steps to align with ISO standard 10993 biocompatibility. Outputs as high as 3.4 liters per minute at 40 beats per minute, with 5.0 liters per minute projected at 60 beats per minute. This mimics the native heart stroke volume of 70 milliliters. Finally, we have an 83% ejection fraction for hemolysis purposes.
Qualitative preliminary CFD validation on our first Pulse 3 iteration has begun to test hemolytic capabilities and flow patterns. Blood damage is a factor of exposure time and shear force, which we estimate to be low. Pressure is seen in the figure, showing the exit points and the points of high and low pressure. The rail reduces contact points and decreases hemolysis points, and the shuttle gap size within the housing will be iterated to balance flow rate and blood damage. To validate our low blood damage, hemolysis testing was started. This year, we were able to run 6 bovine proof of concept tests on Pulse 1, aiming to comply with the ASTM standards. Through centrifuging and separating red blood cells and plasma, we can measure the release of hemoglobin within the separated plasma. As peristaltic pumps have high blood damage, our new novel pump will decrease this challenging issue in industry today. Each model of Pulse has made steps towards getting smaller. Pulse 3 is 3 times as small as Pulse 2, with double the stroke volume. Pulse 3 is also half the size of the native heart, with the same stroke volume.
From this, Pulse 3 meets all key design requirements. Its frictionless maglev system ensures low power consumption and minimal blood damage. The projected flow rate mimics that of the native heart, achieving pulsatile flow with 70 milliliter stroke volume. And at 318 milliliters, we easily fit within the pericardial cavity. Beyond the pump, Pulse is connected to a holistic electrical system. Novelty is in every component. From the custom battery array to our app, CBU Cardiac is building the most advanced electrical system they can. As percutaneous driveline infection is the #1 reason for patient readmittance, we have officially partnered with Invivo Power to build a highly effective TET link. Utilizing a toroidal ring instead of a parallel plate, Invivo TET maximizes power efficiency, minimizing heat generation. We're able to output as high as 30 watts of power at 95% efficiency, making us 3 times as power efficient as commercially available resonant link. To address power needs, we're developing biocells to convert internal energy to electrical energy, aiming for a fully self-contained pulse within 5 to 10 years. Meanwhile, a flexible Kirigami-based battery array offers 24-hour charge, wearable on the arm, waist, or leg, with an internal emergency battery for disconnection situations. Finally, our app, Pulsefinity, is good for daily data logging for doctors, oxygen concentration, flow rate adjustment, and automatic emergency assistance.
Some of the limitations that we've encountered include limited CFD. This is due to a lack of infrastructure. We are currently building our CFD simulations for hemolysis, pressure, and fluid flow. Another limitation is our magnetic levitation system is limiting our flow rate. This is due to magnet slipping, and this is being mitigated by our Hall back array. And finally, for our mock loop, we are using water validation for all of our flow rate calculations instead of a viscous fluid.
Our pump will progress through component level improvements. Magnet slipping was the main issue for our limited flow rate, so we will decrease the gap between each magnet and introduce a Hall back array to mitigate this. We will also use mechanical low hemolytic valves, such as the Medtronic open leaflet valve. We're also developing our own custom tri-leaflet valves, and we will compare the efficacy of both. Next generation pulse will be optimized for anatomical fitment using Vertana AV patient, and hemolytic simulation CFD will be used. All of this brings us to a technology readiness level of 5.
Our magnetic levitation system will both suspend and drive the shuttle autonomously without the need for a motor. A proof of concept linear rail is currently being manufactured, which is capable of moving the shuttle in an oscillating motion, and this brings the project to a technology readiness level of 2.
Okay, so now I'm going to talk about our leadership style, what we did, and how that worked for us. So the main thing that we have is president, vice president. This was something that we adopted from some of our other teams on the university, and it's something that we really like. This is kind of comparable to team lead and co-lead, but we put a lot of care into choosing the vice president because we hope that they would replace the president, and it just kind of gives them a trial period. Knowledge transfer is also really important, and so by giving the vice president as much time as possible to kind of soak up from the president, it offers knowledge transfer. We also end our season after Japan, and so then that gives us a whole semester and a half for the president to be senior advisor and then vice president to become president. And so it kind of gives a buffer before and after for vice president coming into their new role. Under the president, vice president, we started with 4 sub-teams, electrical, mechanical, research, and business. However, as our team grew, we started with only 6 members, and then we grew to now over 50. We had to kind of grow our leadership with our team as well. So looking at this year, this is what our leadership looks like right now. This year we have 1 general weekly meeting with each sub-team has to meet on their own specifically, and then we have a leads meeting as well. So the president, vice president is then delineated into systems, so the design, research, and PR system, which are then delineated further into the mechanical and electrical teams. And then under that are projects. And so a project lead would be in charge of valves, pumps, CFD, or hemolysis. And then they report to like the mechanical team lead and then the design system lead.
For future leadership, it's pretty similar to how we have Pulse 3. We're just changing a couple of things. We now have design as its own sub-team. So as you can see, we have mechanical, including projects such as the pump, materials, and all of our in vivo test benches. We have design as our future CAD, and this is more for anatomical fitment, as well as all of our in silico testing, which is CFD and FEA. For electrical, we are continuing with our maglev system, battery and control system, and this will also go hand in hand with all of our test benches. And finally, we have our research team working on hemolysis, as well as our blood loop, and researching energy harvesting, as well as documenting all of our research within what we like to call the Heart Bible. So thank you, and thank you to all of our sponsors and all of our advisors.
Thank you, Team CBU. That was a nice presentation. And yeah, the questions will be posted to you like at the end of all the presentations as well. Yeah, sure. Thank you. And moving forward, we are having Mending Broken Heart for us to give their final presentation. Over to you guys.
Yeah. Share my screen. So, hello everyone. I'm Hannah, the project manager of Mending Broken Hearts, and presenting with me today is Ria, the systems co-lead. So, we're a team from the University of New South Wales from Sydney, Australia, and together we make up 20 undergraduate students from a wide range of engineering backgrounds. In Australia, heart failure accounts for almost 1 in 50 deaths, equating to around 9 people losing their lives each day. However, the solutions in the market for this are very limited and are only temporary replacements for patients as they wait for a donor heart that may never come on time. And so no matter what solution you choose, the experience of relying on a mechanical support device can be extremely daunting and an unnerving experience for not just the patient, but also the clinicians involved. Thus, this year, we made it our mission to develop a destination TAH that truly centers on the needs of both patients and clinicians, making this life-changing journey as smooth as possible. Thus, we established a set of design requirements to guide our design processes. First, our heart must function, have the essential functions of a natural heart to ensure sufficient perfusion throughout the body, whilst being durable, biocompatible, and being so that it can function reliably over time without adverse reactions. We also have our non-functional requirements that reflect our mission to be user-centric and also target a lot of our unmet needs in the current TAH market. So for example, our design prioritizes being lightweight, minimizes noise, and has the ability to adapt physiologically. It also offers real-time monitoring to detect, respond to, and record changes in the patient's condition, allowing clinicians and researchers to export data for further research, all while emphasizing data security and protection.
So our design incorporates Hazel actuators, which is a new technology unprecedented in circulatory support, which basically expands when a high voltage is applied and returns to its initial shape when the voltage is removed. These actuators are then used to induce contractions of 2 soft chambers, which contain the blood. These components are housed in a rigid shell with silicon valves to ensure unidirectional blood flow. We've decided to house each side of the heart in a separate rigid shells, creating a modular design that facilitates easier implantation and adjustable orientation to fit the unique anatomy of each patient. In designing the shape, we focused on maximizing displacement of Hazel actuators while avoiding organ interference and preserving the atria to keep future heart transplants viable. We evaluated the anatomical fit of our designs using Autonomy V patient simulations and plan to seek further input from surgeons at St. Vincent's Hospital to refine implantation procedures. While our current prototypes are 3D printed, our next steps include investigating lightweight, cost-effective, and biocompatible materials that meet clinical safety standards. So currently, our soft chambers are made from silicon, and they are hand-painted inside 3D printed molds. And future work includes investigating surface modifications with PEG or PVAM for improved hemocompatibility before conducting fatigue tests, which is followed by hemocompatibility testing at the Victor Chang Heart Research Institute. In our prototype, silicon umbrella valves are used to ensure unidirectional blood flow, and future work involves collaborating with the valve team at UNSW, who are developing tricuspid valves made from silk. But what really sets us apart is definitely our actuators. These pump the blood without the need for motors or pneumatic drivers. They're made from cheap, accessible materials, and they are lightweight and operate silently. With a higher power density than human muscle, our actuation allows for controlled variable motion for fine-tuned blood dynamics. The actuators themselves consist of a flexible polymer pouch containing an insulating liquid dielectric and a pair of electrodes positioned on opposing sides of the pouch. So when a high voltage is applied, these electrostatic forces draw the electrodes together, which displaces the liquid inside and alters the shape of the pouch. So once the voltage is removed, the dielectric quickly self-heals and the pouch returns to its original shape. In developing the Hazel actuators, we have explored various materials and manufacturing techniques. Our current method uses a modified 3D printer with a copper head to heat seal the BOPP films into circular pouches, which are then filled with distilled water and fitted with carbon electrodes. We have tested different volumes of dielectric and evaluated potential displacement. And additionally, we have conducted heat sealing using a linear actuator to assess durability. By collaborating with Artemis Robotics and using the university's high voltage lab, we have verified Hazel's technology, though it does currently have a limitation of only 8 millimeters displacement. So our current focus is on improving this by replicating 100% plus strain, which has been achieved by others. However, we have not yet observed measurable force or displacement due to air bubbles in the Hazel, which definitely limits the voltage to 4 kilovolts to avoid dielectric breakdown. So in order to enhance displacement, we must find a method to remove the bubbles, increase the dielectric permittivity, and use lighter electrodes with more surface area, as well as stack the Hazels. Hazel also faces two main challenges. First, it requires DC high voltage, which is incompatible with transcutaneous power transfer mechanisms that do require AC. So future steps may involve integrating an AC to DC converter and a high voltage amplifier within the body. And second of all, high voltage poses, of course, safety concerns, making regulatory approval difficult. So we will have to explore something called HAV actuators, nanotubing, carbon nanotubes for better capacitance and insulation for wires to reduce voltage and ensure biocompatibility. Due to safety concerns, we cannot yet test the Hazel actuators directly in a mock loop. So instead, we have modeled the Hazel actuator motion with a linear actuator in order to assess our device's flow rate and pressures. We have reached initial flow rates of 2.5 liters per minute at 12 millimeters of mercury. However, we were limited by the speed constraints of our linear actuator. From this, we do estimate our Hazels will need to operate at 120 BPM or 2 Hertz to achieve a flow rate of 5 liters per minute. Our main concern with this is that while Hazels only have a roll-off frequency of 120 Hertz, a higher frequency will require faster prefill and will also result in an increased risk of damage to the blood cells. Our device focuses on 3 electrical areas, providing controllable input to the Hazel, monitoring health of the patient, and relaying data to clinicians and patients via an app. We created a PCB schematic for Hazel input with a microcontroller, which manages the voltage regulator and optocouplers, acting as switches for the actuator. This design is compact and ensures the microcontroller from high voltage for safer communication with the app. However, commercial high voltage optocouplers are definitely costly. I think it's around $400 each. So we do plan to manufacture our own to reduce these costs. For patient monitoring, we use force-sensitive resistors to estimate blood pressure and a Hazel extension sensor for actuator control and real-time displacement data. The sensor's capacitance increases with extension, which our microcontroller translates into extension levels, and testing and further development for sensing blood oxygen and flow rate are definitely ongoing. The app, which is designed in Figma, has 2 sections. So one is for patients to monitor battery life, track appointments, and input data, while the other is for clinicians to view health key metrics, such as flow rate, blood pressure, and feedback from St. Vincent's Hospital staff who have worked on other devices such as HeartMate 3 and Bivacor TAH, has guided the app's user-friendly design that seeks to include patients from all age groups and technological literacy. However, Bluetooth compatibility does raise cybersecurity concerns, so future work does include user trials and further app development.
The MBH TH aims to initially target the Australian market, leveraging the $50 million government-funded Artificial Heart Frontiers program. This initiative provides opportunities for research, collaboration, media coverage, and technological advancements. Key beachhead Australian target markets include hospitals like St. Vincent's and Prince of Wales, where existing clinician relationships offer credibility and clinical support for our TH development. After establishing a presence in Australia, we plan to expand into the global market, valued at around 1.87 billion USD. However, regulatory approval is required before market entry, so the primary focus for us is to pass the TGA approval in Australia, which involves Class 3 medical device regulations for the TAH and its accompanying app. So the total cost for just TGA approval for both the app and the heart is estimated at around $140,000. So taking that into account with the estimate costs of bringing our app and TAH into the Australian market, we estimate that our TAH will cost around $130,000 as a one-time purchase, with ongoing maintenance expenses ranging from $130K plus, depending on the device's lifespan. So now I'll go into our team structure. So our team operates as a hybrid structure under the UNSW Vertically Integrated Projects VIP program for our technical team and the ARC Club system for our non-technical teams. So those unfamiliar with VIP, it's an academic initiative at UNSW, so our university, that allows students to participate in multidisciplinary research projects for credit. So, however, one of the challenges we encountered was accommodating for students who couldn't enroll in VIP, whether they had no elective space left or postgraduate students who were unable to join for credit. So we allowed for extracurricular participation. This way, we retained talented members who might have otherwise been excluded. And this inclusivity has not only strengthened our team, but made MBH accessible to those who are passionate about our mission. On the technical side this year, our team included 3 core sub-teams: mechanical, electrical, and software engineering. However, next year, we plan to establish a systems team, which serves as the bridge between these sub-teams. This team will focus on ensuring integration across the hardware and software components, a crucial step as we approach more advanced stages of development. So Ria, who's presenting with me today, is one of our systems co-leads for next year. On our non-technical side of the team, we have these 3 sub-teams that are all under the UNSW ARC Club system. And so this way they can receive recognition for their efforts despite being extracurricular members. So how does MBH actually function? So we have our weekly meetings for the whole general team, and that is the backbone of our team management strategy. We also have separate technical team meetings that allow for focus updates and brainstorming. And back to our general whole team meetings, these meetings also include our academic advisors and our PhD mentors who help give us a lot of feedback as we plan the week ahead. We also have drop-in workshop sessions that are run by our team leads, and this has played a key role in fostering teamwork and cross-disciplinary learning, ensuring that no one is left behind. Our success has stemmed from a few key strategies. Firstly, we've defined clear goals. So from day one, we aligned every decision with our mission to create a user-centric TAH. And second, we used resources effectively. We maximized UNSW's facilities from makerspaces to mock loops and sought feedback from clinicians and advisors. A key lesson we learned here was not to hesitate in asking for help. Once we reached out to the clinicians at St. Vincent's Hospital, the progress that we made with our app had skyrocketed. And so looking ahead, I'd like to share some advice for some future teams. So first, prioritize organization and communication. Establishing clear structure with defined roles early on really helps to guide people so that everyone knows what the responsibilities are. Leverage mentorship. Your universities will be filled with researchers and experts who are eager to share their knowledge, so it would be good to take advantage of that. Foster inclusivity. Make sure everyone on the team feels valued, as a supportive environment will help you retain talent for future leads and maintain morale. Embrace flexibility. Be prepared to adapt because, for example, this year, our software team was only created halfway through the year to meet the increasing demand in developing our app. And secure funding early. So building relationship with sponsors and university administrators as soon as possible, because some companies set their budgets at specific times of the year. So you have to be very key with your timing when sending your prospectus, as this can increase your chances of success. And lastly, celebrate wins and learn from failures. Recognizing achievements keeps the team motivated, while analyzing setbacks can help you improve. Our experience in the Heart Hackathon has been both challenging and rewarding, and we're really proud of how far we've come. This project was only made possible through the commitment of our sponsors, Abbott Office of Chief Scientist Engineer, and the collaboration of clinicians and research institutions. Thank you.
Thank you, team Mending Broken Heart, and it was a wonderful presentation. And thanks for the key points. For it, it'll be useful for the new teams, for the new joinees and staffs. So, any questions to any of the teams, guys? Like, please feel free to ask any questions to any of the teams.
Yeah, feel free to raise your hand or type in the chat or submit in the Q&A. We did have a couple questions submitted ahead of time. So I guess for each team, one of the questions was, what was a challenge that surprised you the most in terms of difficulty and time? And how did you overcome it? Broad question. Potentially people need to think about. So maybe if someone's willing to jump in instead of throwing someone under the bus.
I can say a bit about Bath Heart if you like. I think one of the biggest challenges that we weren't expecting because of our success as a team last year, we didn't expect so many people to rush in to join. So we ended up with a massive team, a terrible handover, and yeah, just a big mess to deal with at the start of the year. And I think one of the ways we tackled that is uh, strong leadership and getting a team structure sorted out pretty fast. And that really helped us to get the ball rolling again. Obviously, it was amazing to have all the success of last year, but then when everyone came back, everyone was so overwhelmed in their final year. We didn't get to hand over a lot of information, but we learned from that really well. And the handover that we've done this year has been a lot more successful, or I hope. And I think that the new team has got started a lot faster than we were able to last year. So yeah, that's one of the big challenges for us.
Yeah. Could you elaborate a little bit on the handover process? Because I know it's one of the hardest things that's kind of been emphasized by many teams.
Yeah, talk about that if you want, Finn. So we've spent a lot of time basically promoting the team and explaining what it's actually about. So we did a couple of meetings before assigning any roles. And then following that, we created a like detailed sign up form and an interest form. And this was all the roles that we had available. And we went into even more specific roles so that people could get an idea about what each individual team has to offer and the skills needed for that and the dedication and whatnot. So we really, I think explaining what actually goes into it really helps, and breaking it down for people helps. And we promoted it to people, and they signed up accordingly. And from that, we then did rounds and rounds of interviews. So I think the mechanical leads, they spent maybe like 8 hours doing interviews, like in one day. I interviewed a couple people for the team lead position, and each of the leads interviewed like whoever they thought was appropriate based on that form. So that's something different that we did from last year, because last year they didn't do any interviews. The only one that was interviewed was me for the team lead position, and the rest of them were kind of just handed over. So I think that really helped, and we put a lot of time and effort into picking sort of the right person. And if needed, we've explained to them that things are going to change, that things can change, that you can switch between roles, and sort of just explain what happened with us, and all the possibilities that can happen. And then when it came to handing over, each of the leads was responsible for like handing over all of the work that they've done, and all of the like they had presentations or they had whatever format they have. And we're still sort of in the process of handing over because we're attending their technical meetings or their commercial meetings to make sure that they sort of have a hand in play. But yeah.
Great. Anyone from CBU that would like to make a comment?
I can start. So for us, one of our major challenges was that we went from this transition from peristalsis to our new pump design over the summer. And so through that summer gap, we had a lot of issues in communication or just that knowledge transfer, similar to Team Bath, where it's making sure that everyone's on the same page and making sure that everyone exactly like knows what's going on. And so moving into our fall semester, all of that kind of innovation over the summer was hard to kind of get other people caught up and on the same page because of our summer break. And so moving forward, we're looking into better ways to articulate our information. We also have the Heart Bible that has a lot of information, but just emphasize the clarity of communication and just what we're all about for new people and stuff like that.
Yeah, I guess a question relating to that is like, how did you decide to pivot? As in, was there like people that were still exploring new ideas while others were like continuing with the existing idea? And then how did you pro con it, sort of thing?
Yeah, so Gianna can share some of her research into tubing, but ideally over the summer this last year, we dove into degradation of tubing and what that would look like in a peristaltic pump because last year we had a lot of issues with just the use of tubing and what that looks like with kinking and just pressurization of it. And so we had some people working on that prior research, and then we had other people looking into new designs and future developments. And that's how we went into the shuttle system with the magnets, which will allow for the lack of tubing and more of a smoother design in that sense.
Great, thank you. Mending Broken Hearts.
I can talk about our challenges. So I guess our challenges are a bit similar to CBU. Like we changed our design from a rotary pump to our Hazel actuators. And I guess that stemmed from the fact that we didn't want to, we knew that if we were going to stick with rotary pump, it'd be very hard for us to stand out amongst other teams that are also doing that and also amongst the people like companies in the market that have already dedicated like years to that research, like Bivocal, for example, with their maglev. So we wanted to try something different, especially as a student team. Like this is, we have that opportunity and that freedom to try other things. And like, if it doesn't work out, it's fine. It's not like, we're in a startup, and like, like we're spending our money on it. Like, not really. It's like a student project with the university backing us. So it's like a good opportunity to try new things, and figure out something that's a bit different. And I guess we also had a bit of a challenge with like onboarding new people at the beginning of this year. I think it took nearly like a whole term for the new members to start to feel like they understood everything that was going on. I think because we didn't have a proper structure in terms of onboarding everyone, and also because I'm the project manager, but I wasn't there for term one because I was on exchange. So it was a bit difficult managing everything in a different country on the other side of the world. So I think it um started getting a bit better in term two, and then people were a bit more comfortable in the team. But like next year, definitely we're trying to make like a proper structure on onboarding people. Like one of the things we're thinking about is because we have VIP as one of our um uh, ways that our technical team is run, we're thinking of actually having a quiz that's like weighted, like they get graded on it on like different facts that they need to know about like TAHs and our heart and the market, so that it gives them motivation to learn all the content really quickly and early, before we get started on actually developing our heart. So yeah.
I guess related to or open to all teams was there was a question here which was how long did you allocate to the research phase before moving on to prototyping and testing? But I guess more broadly, I know it's changed potentially from the first year of the competition to the second year of the competition, but like imagining a timeline, like how many months or things was allocated to ideation versus software simulations to trying to make a physical device.
I can talk
Um,
about that.
Yeah, you go first. It's fine.
Okay, sure. So like I was saying, it took us a whole term to figure everything out. And so that included research and figuring out what our device was actually going to be. So I guess like research and ideation and everything all took a entire term. So for reference, one term for us is around 10 weeks plus like 3 weeks for exams. So like I guess 3 months-ish. And then the next term, like term 2 and term 3, so like the rest of the year, we spent that whole time actually like developing our prototype. So we didn't do that much like CFD. We mainly did like 3D printing and testing in the mock loop. Yeah, so we just like made different different variations of our prototype for the rest of the year, basically.
Yeah. So for us, we kind of had a similar thing, but we had approximately 1 to 1.5 to 2 months of ideation and research and concepts and testing out different concepts. And then we move on to simulations and then prototyping for the next few months. So that phase is obviously much, much longer once we have a final design that we've chosen. And then the last few months, but leading up to the competition was approximately maybe like the whole of summer. So I would say 3-ish months we were testing and trying to get our MCL working. So that's sort of the timeline we have. And in the meantime, we also had sort of our prototype being made as we had it done externally for the casing at least. So that's being done on the side. So sometimes it's in parallel as well, as along with the simulations. And yeah.
CBU?
Yeah, for CBU, it's very similar to what Nancy was saying, how we kind of have projects in parallel working at the same time. We kind of bounced off of last year with our peristaltic pump with Pulse One. And from there, we kind of followed that trajectory. And at the same time, we have a separate team working and researching on the side for that peristaltic pump, as well as looking towards the future. And that's why this year for our leadership style, we want a very specific designated team for our design process. So we will be continuing, like Vinci said, with our kind of parallel research, but it also kind of depends on the project. If we need more hands on a certain project, we kind of shift. So we try to stay fluid in what we need and the project at hand.
Yeah, to add on to that, we also have a research team. And so they're continuing to come up with new ideas and new iterations or just new things out there in order to implement or iterate into our design as well.
Okay. Let me share my slides. Okay. So as mentioned in the finals, we hopefully are going to have 6 new teams starting next year, as listed there. And then I'll be talking through kind of some of the things that we're planning to do to address the feedback that was given in the finals and support the newer teams. So as some of you may be aware, within the website, which will get updated, we have this central page kind of as a competition guide. And one of the things that at least some people aren't aware of is that we have this tab here called resources and documentation, which includes things like advertisement documents. But one that might be very useful for new teams is that we have this scientific overview that gives kind of like what is the market and some basic biology and engineering that was created by the Monash Heart Hack team, basically, that's been shared. So kind of in response, there was quite a lot of feedback in having a kind of central Slack or Discord. So we've created one I've put in the chat and we'll send an email about it, where hopefully we'll get some more engagement between teams and with us, the organizers and teams. So to talk through the idea of it is that we will be hopefully sharing, or anyone can share potential work opportunities, whether they be internships, research, PhD, or whatever. Um, and then additional resources, whether they be cool related news in the total artificial heart space. Then the events, the idea is that hopefully teams will either suggest events that we could organize or advertise their own events if they're being held in a webinar or hybrid format, and we can promote and get teams to attend each other's events. And then this events will create new channels for upcoming events to discuss them and have input on them. Then the competition section, one of the things which is more just to help us keep track of people and at them, is that there's this join a student team little channel where if you react to the right icon, it will automatically assign you the role of the team that you're from, which will allow us to get access to a private channel to talk with you, but also just allow us to at the team when we're reporting successes or news from that respective team. But similarly, teams can report their successes here in the student team news, ask questions, and assessments will have a lot of comments and things to discuss. And then there's just a general chat as well. So that's what we're hoping to move forward with, to have some more engagement between us and between the teams. We have case studies, so thank you to University of New South Wales and CBU. Both have created case studies kind of talking about how their team was structured, kind of like what they presented a bit already today. And we're inviting all teams to do this as well. So we'll be in contact via email, and we'll eventually upload these on the website, but we'll share them in emails as kind of reference so that we can get different teams' perspectives. Because as highlighted, some are within a university course, some are standalone clubs, some are honors projects. So it's good to hear the different perspectives and all that there. Then I believe the rule that we set, hopefully I'm not mistaken, is that alumni is 1 year out of their degree are still allowed to support the existing team to help hand over and everything. But something we would like to have is alumni create kind of an advisory board for the organizing. So the idea is that there's a Discord, and then there's going to be a role for alumni advisors, and teams can ask them questions because they have advice on how teams are structured and all that. The hope is potentially, because we're all in very different time zones, to maybe have events more regionally focused to be better, and to get them to provide feedback on existing and new initiatives. So the idea is, at least to begin with, the minimum requirement is 3 meetings throughout the year, where we're going to try to organize one in the middle of January. And if anyone from your teams that's graduating is interested, we'll also send an email out. But if you contact us, we will try to arrange a time for that. And then depending on how keen alumni are, the idea would be potentially to have sub-teams to focus on a particular project to improve a component of the competition itself. Yeah. As many of you know, I'm going to go back a couple pages, is that we have advisor consultations, which are kind of hidden in this private content, which has a password for registered teams, which you can send an email if you don't have that password. But within that, there is access to booking advisor consultations and everything to support teams. And I know some people have submitted suggestions for different sorts of advisors, and we will try to look into obtaining them. Yeah. So in terms of timeline, the key ones are same as the last 2 years, which is the preliminary report start of April, finalists announced 1st of June, final report 1st of September, and grand final 30th of November, the day before ISMCS in Vienna, Austria. Kind of based on the feedback that teams have given is moving away from workshops that are just direct presentations and going towards more of a forum-like activity. So hopefully it will take a bit of work and interaction with the teams. The idea is that in February would be a design forum. It would be over 2 or 3 sessions so that we cover a couple of different time zones where we bring in relevant experts that can kind of hot desk help, but hopefully also have teams themselves either support other teams or provide advice or key learnings. So the idea would be 1 February would be focused more on the design and technical, and then because that's what the preliminary report is largely judged on. Then we would have what we've done previous years is total artificial heart symposiums kind of later in April after the preliminary report for teams to share their progress and receive some feedback. And then in July, more relevant to the final report, is have a business forum where the discussions are more on the IP regulatory and getting help around that. And then in September, around the World Heart Day, is to have a careers webinar where we either invite people that are working in the total artificial heart space, or hopefully, as we build more and more years, is invite some people that participated in the competition that have now gone on to do research, work in industry in the relevant field. And then December is the event we're doing right now, is the closing webinar. So the idea is, pending feedback and its success, is that this would be kind of the bare minimum plan, where this is kind of like the guaranteed year on year, this is what happens. And the 3 kind of forum are supposed to be kind of interactive, and there's this careers thing talking about the future. But interspersed, the hope is that either through team suggesting or through us, we'll also add in actual webinars. But we were trying to kind of up with a yearly structure that is constant and has a bit more interaction there. I will then pass it on to Madhu.
Thanks, Ethan. So I'm gonna tell you about the registration process. So most of you are aware of the process, like how to register and the team and stuff. So it's the same almost. So the team, each participating team should have 1 academic advisor and 1 to 2 team leads. So the one which we added this year is like we would like to have 1 person that nominated from each of your team. It's like a representative of your team. So it will be like a point of contact between the team and the organizing committee. So the idea is that will facilitate us to run the competition even much smoother and better. And second, we want to tell you about is we expect everyone to submit, like every team to submit 2025 entry form. And the next other one we want to mention is like the registration fees is up this year. Before it was $350, and now we have raised to $750. But it's for the entire team. And we also want to mention that this includes the ISMCS membership for all the team members this time. But before it was just for 5 members per team, but this includes for all the members, like even if it's 10, 15 members per team. So everyone will be getting the membership for ISMCS particularly. And next, we encourage everyone to individually to fill up the demographic forms. So next is the challenge statement.
Yeah, I guess
If you have any question in the registration, just feel free to ask.
Yeah. So to highlight that, we'd like hopefully all teams to submit new 2025 entry forms, and when we give it the demographic forms kind of as soon as possible, so we can create new mailing lists and keep that up to date. Whereas the membership fee does not exist yet, so you can't pay that right now. That's still being set up, but the deadline for that is the preliminary report deadline.
Yeah, that's true. And the other one we would like to add is the challenge statement. This is a new addition to the competition, and we are aiming to have new challenge statement each year. And for this year, the potential statement is addressing underserved population and how can your device be rolled out to the lower income countries. So this is the broad statement, and the few potential considerations are, I mean, given in the slide, like you can either concentrate on cost, regulatory requirements, barriers, environment, or different demographics and level of activities. These are just the ideas, but feel free to pitch in any of the ideas that you have. And the overall criteria for the awards remains the same. And but just the weightage of the award will be differ. But apart from that, everything is same. And we'll be having extra 10 points for the challenge statement. And there'll be a special 2 awards this year as well. So one is for the challenge statement, and the other one is for the best newcomer award. And also, sorry, one more award. So that is the most advanced design. That's similar to the previous one. And as you guys gave the feedbacks, we'll be trying to get the rubrics out soon this year. So it will be easy for you to work along on this. And so if you have any questions in the challenge statement or how to work on it, just feel free to ask now or in the web, just send the email to us. We'll be happy to address it. And thanks to the organizing team. So without them, it will be so hard to keep this event up and running throughout the year. And if you have anyone have any questions on the new format or any challenge statement or how to proceed with it, please let us know. So really.
We had a question regarding the demographic forms for next year. So the entry form that's there, there's a Google form and the like normal one that you fill out and compile as a PDF. Should we do the Google form and wait for everyone to do the Google form before we submit the entry for the Heart Hackathon? Like everyone in the team to submit that Google form?
We want everyone in the team to submit the Google form.
Yeah.
Like the democratic form, and one form for the team. Like the entry form is just for one. Like as a whole team, you can just submit one form, and democratic form you have to submit like individually. So
and they can just do that after we've submitted the one form. Okay, perfect.
Yeah, that's right. Yeah. Cool. Any more questions, guys? Okay.
I guess if that's the case,
yeah. Go ahead. Yeah.
Yeah. Oh, thank you for everyone attending. Thank you to the 3 winning teams, but to all 9 teams who've made very amazing progress, and we're looking forward to seeing what happens
that's true.
next year.